In this video, we're going to cover a few examples related to Taylor and MacLaurin series. We're going to start with example 1 here, and we're going to write out, we're going to find the MacLaurin series of the function f of x equal to e to the x and its radius of convergence. In other words, for what values of x is our MacLaurin series actually equal to e to the x? So we're going to let our function f of x equal e to the x. And recall that to find our MacLaurin series is defined as f of x equal to the sum of the series n equals 0 to infinity of the nth derivative of f evaluated at 0 all over n factorial x to the n. So let's calculate that now for this function. Well, to do that, we need to find the nth derivatives of x. First off, the 0 derivative of x, of f of x, is e to the x. The first derivative of f of x is also e to the x. The second derivative is also e to the x. And the third derivative is also e to the x. And in fact, this continues forever. What do we actually care about? We care about those derivatives evaluated at 0. So what is f of 0? Well, that is 1, because we get e to the 0, which is 1. F prime of 0 is also e to the 0, which is 1. And this is true forever. So in fact, if we write out our MacLaurin series, we get that f of x equal to e to the x is this series up here. If I plug in n equals 0, I get 1 over 0 factorial times x to the 0 plus 1 over 1 factorial times x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed, and so on. And if we write out what this pattern is, this pattern tells us that e to the x is equal to the sum of the series from n equals 0 to infinity of x to the n over n factorial. And so this is our MacLaurin series for e to the x. And now, for what values of x is this true for? Well, for that we find the interval of convergence for this series, and we can use the ratio test for that. So we take the limit as n goes to infinity of this series. So we get the absolute value of a sub n plus 1, which is x to the n plus 1 over n plus 1 factorial, divided by a sub n, which is the same as multiplying by the reciprocal of this, so that's n factorial over x to the n. And this is the limit as n goes to infinity of the absolute value of x over n plus 1, right? N factorial over n plus 1 reduces to just 1 over n plus 1. And x to the n plus 1 over x to the n just reduces to x. So we can pull out the absolute value of x in front of our limit. And we take the absolute value of x times the limit as n goes to infinity of 1 over n plus 1. This limit is 0. So this whole thing is 0 for any value of x that is always less than 1. So this tells us that for every value of x, our ratio test to the limit of that goes to 0, which is less than 1. So for every value of x, our series is convergent. So our radius of convergence is infinity, or our interval of convergence is negative infinity to positive infinity. And so we now have a way to write out that function e to the x as an infinite polynomial, or in other words, a MacLaurin series, which is a special type of a power series. What can we do with that? Well, for one, we can integrate e to the x squared now. So we are going to find the integral of e to the x squared dx as our second example here. So how do we do that? Well, recall that e to the x is this series right here. So that is n equals 0 to infinity, x to the n over n factorial. And so, what is e to the x squared? Well, here we replace x with x squared. So this is the series from n equals 0 to infinity of x squared raised to the n all over n factorial. Or in other words, the series from n equals 0 to infinity of x to the 2n over n factorial. Okay. Now for this, what do we need to do? Well, I wanted to integrate this. So let's integrate e to the x squared dx, which means we integrate this right here, the series from n equals 0 to infinity of x to the 2n all over n factorial dx. But let's integrate each of those terms. If we integrate each of those terms, we integrate x to the 2n with respect to x. So this tells us that each of our terms is x to the 2n plus 1. And of course, if we integrate, that means we add 1 to the exponent and divide by that new exponent. So we get 2n plus 1. And we still have that coefficient of 1 over n factorial, so we still have that n factorial in the denominator. And of course, we take all of that and we integrate it, so we add a constant c to the outside. And now we have an integral in a power series representation of e to the x squared. And the neat thing about that is previously we had no way to integrate that function, and now we can do that. Okay, we'll stop this video here, and I'll have another video with a few more examples.